You bite into a seedless watermelon, sweet, red, and you don't have to worry about spitting out seeds with every bite. But stop for a second and think, if it doesn't have seeds, how does the next watermelon grow? A fruit that can't reproduce through seeds should have disappeared from the planet decades ago, and yet it's still on your table year after year. We treat seedless watermelon like it's the most obvious thing in the world. You go to the grocery store, it's there, you buy it. End of story. But think about the basic logic of any plant. An apple has seeds to grow into an apple tree. An orange has seeds to grow into an orange tree. A seed is the instruction manual that creates the next generation. Take away the seed, and you've just cut off the plant's future. And yet seedless watermelon never disappeared. It's sold by the millions all over the world. The answer involves a laboratory trick from the 1930s, a poison extracted from a flower, and a plant growing right in the middle of the field. First, we need to be honest about one thing. A seedless watermelon isn't completely seedless. Take a closer look next time. Those tiny white soft little specks that you swallow without even thinking? Those are seeds. Sort of. They're seed coats that started to develop and simply stopped halfway through. They ended up empty. They never matured, never hardened, never became those hard black seeds capable of growing into a new plant. They're called rudimentary seeds, and they're perfectly safe to eat. So the fruit isn't sterile because it has no seeds at all. It's sterile because the seeds it tries to produce are essentially born dead before they ever truly exist. The absence of seeds isn't a defect, it's intentional. Someone designed this plant to fail at exactly one thing, and only one thing, making viable seeds. To understand how that happens, we need to dive into the recipe of chromosomes. And that's where a poisonous flower enters the story. Every plant, every animal, including you, carries chromosomes in sets. Think of a chromosome as a cookbook. Inside it are the instructions for building an entire organism. A normal watermelon, the kind that's packed with black seeds, has two sets of that cookbook. One came from the mother plant, and the other from the father plant. Two sets. Scientists call this diploid. Di meaning two. In a regular watermelon, those two sets add up to 22 chromosomes in total. 11 from the father and 11 from the mother. Perfectly paired, like two copies of the same cookbook sitting side by side on a shelf. And that pairing isn't just for show. It's essential for one thing, making seeds. Picture a line of people dancing in pairs. When the music stops, each pair splits up. One dancer goes to the left, the other goes to the right. Everyone has a partner. Nobody gets left behind. The split is clean, symmetrical, perfect. That's how nature builds a healthy seed. Chromosomes paired up, separating into orderly pairs. Now imagine what happens if someone throws that whole process into chaos right in the middle of the dance floor. That's exactly what a Japanese scientist deliberately did. The 1930s. A Japanese geneticist named Hitoshi Kihara at Kyoto University is studying how to manipulate these sets of chromosomes. He wants to do something that seemed to go against nature, create a plant that couldn't produce viable offspring but would still bear fruit. And he uses an unlikely weapon, colchicine. Colchicine is a substance extracted from a flower called the autumn crocus. At the wrong dose, it's toxic, but in the right hands, it does something fascinating. And pay close attention here, because this is where a huge misunderstanding comes in. Seedless watermelon is not genetically modified. According to current scientific understanding, it's the result of traditional crossbreeding, the same kind of technique humanity has used to improve plants for centuries, just with a carefully applied touch of chemistry. But what does this toxic flower actually do to chromosomes? When a cell is about to divide, the chromosomes first duplicate themselves and are then pulled to opposite sides by a kind of internal tug-of-war made of microscopic fibers. Colchicine prevents those fibers from forming, dismantling the system that would normally pull the chromosomes apart. The result? The cell duplicates its chromosomes but can't split into two cells. All the copies end up trapped, piled together inside a single cell. Suddenly, that watermelon that used to have two sets of chromosomes now has 4. 22 becomes 44. Something new is born, the tetraploid watermelon. Tetra, meaning 4. It grows, it lives, it flowers. It's a perfectly functional watermelon, except it carries twice the genetic paperwork inside. And here's the clever part. Kihara didn't want the tetraploid as the final product. He wanted to use it as one piece of a very specific cross. So what happens when you cross two numbers that don't match? A useful freak of nature? Now Kihara has two plants in his hands. On one side, the normal watermelon. 2 sets, 22 chromosomes, the diploid. On the other, the colchicine-boosted watermelon. 4 sets, 44 chromosomes, the tetraploid. He crosses the two. Think about what each one contributes to the next generation. During reproduction, each plant donates half of its chromosomes to the new seed. The diploid, with 2 sets, donates 1 set, 11 chromosomes. The tetraploid, with 4 sets, donates 2 sets, 22 chromosomes. Add them up. 11 plus 22, 33 chromosomes. And that's how the triploid watermelon is born. Tri, meaning 3. 33 chromosomes arranged into 3 sets instead of the usual 2. A perfectly odd number and a perfectly inconvenient one. That triploid seed is real. It exists, it germinates, and it grows into a healthy plant with leaves, flowers, and fruit. But hidden inside it is a sentence that won't be carried out until the most important moment in any plant's life, the moment it tries to produce its own seeds. Remember how chromosome pairs split perfectly? Now try doing that with 3 sets. Imagine you have 3 identical socks, and you need to pair them up before putting them away. You can make 1 pair, but there's always 1 sock left over. Always. There's simply no way to split 3 into 2 equal parts. That's exactly what happens inside the flower of a triploid watermelon. Go back to the dance floor example. Before, every dancer had exactly 1 partner. Now, when the music stops and everyone tries to split into 2 sides, total chaos breaks out. 1 dancer goes left, 2 go right, the next group gets tangled up. There's no fair way to divide them. When it's time to separate the chromosomes to make seeds, the 3 sets can't organize themselves into neat pairs. Some chromosomes are left on their own, unevenly distributed, randomly pulled to the wrong side. The result is chaos. The cells that were supposed to become viable seeds end up with the wrong number of chromosomes, some with extra pieces, others with missing ones. Incomplete instructions, and cells like that never become real seeds. They stop developing halfway through because the genetic information isn't correct or complete. According to current scientific understanding, it's this chromosome imbalance, 3 sets that simply can't divide evenly, that makes the plant essentially sterile. But if it's sterile, how can it still produce fruit? The biggest secret is hiding right in the middle of the fields. Even a triploid watermelon has to be pollinated in order to produce fruit. Pollen has to reach the flower to trigger the signal. Go ahead and start growing a watermelon. So if you planted nothing but seedless watermelons in a field, you'd harvest almost nothing. The flowers would simply fall off without producing fruit. And that's where the simplest, most practical solution in this whole story comes in. Right in the middle of the triploid watermelon field, the farmer plants a few rows of ordinary diploid watermelons, the old-fashioned kind packed with seeds. They're called pollinizers. These plants produce healthy, fertile pollen. Then the bees take over, flying from flower to flower and carrying that pollen from the pollinizer plants to the flowers of the triploid plants. The pollen reaches the triploid flower and triggers the chemical signal. You can start growing the watermelon now. From that point on, the triploid fruit develops normally, big, sweet, and red. The fertile pollen successfully triggers fruit development, but it can't produce real seeds inside the fruit. That's because the triploid's chromosomes are still an odd-numbered set that can't be divided evenly. The signal to grow works, but seed formation doesn't. That pollinizer plant is the real secret. Farmers calculate exactly how many rows of regular watermelons they need to plant among the triploids, just to make sure the bees have enough pollen to spread around. Those plants stay in the field the entire time, and they're indispensable for producing seedless watermelons. So to answer the question, where does the next seedless watermelon come from if it doesn't produce seeds? The answer is, it never comes from a seedless watermelon. Every single crop of seedless watermelons on Earth comes from this genetic engineering process. Seed producers plant ordinary diploid watermelons and colchicine-created tetraploid watermelons all over again, every single year. They cross the two, and it's that tetraploid by diploid cross that produces fresh triploid seeds. Those triploid seeds are harvested, bagged, and sold to farmers. The farmers plant them alongside ordinary diploid pollinizer plants, and that's how the seedless watermelons that eventually make it to your table are grown. What's fascinating is that a seedless watermelon isn't a self-perpetuating variety. It's a product that humans recreate from scratch every single growing season. If this entire process stopped, seedless watermelons would simply cease to exist. You're not just eating a piece of fruit. You're eating the final result of a genetic calculation that has to be repeated over and over again. A fruit that has no future on its own, and because of that, depends entirely on us to keep existing. It's proof that some of agriculture's greatest breakthroughs don't come from giant machines or futuristic technology, but from deeply understanding how nature itself works. That's one of the most fascinating things about science. The more it answers questions that seem simple on the surface, the more it reveals that the world around us is far more extraordinary than it appears.